have are three unknowns. I have, where I unpin it, I have two unknowns. And I also have a two-force member here, BF. By some moments at E, I've got the weight hanging out here, I can get BF for the equation. Okay, number 7. Number 7, what we have are two blocks that are hooked together, kind of a train style. This is going to take two free body diagrams. We've got block B weighs 500 pounds. Block A is. We're going to find the new block A. So I did my two free body diagrams. I've got block B up here, 500 can pull on the tension. Direction is going to be the opposite direction. It is at impending motion. And my other free body diagram is going to be that at a slant. Well, the one here, block B is going to have less unknowns in it than block A will. So I start with block B. Some forces in the Y direction, some forces in the X direction. And I can get T. Getting T is the same T over here on the free body diagram with block A in it. I rotate my coordinate system to this X prime direction. The equation in the X prime direction by assuming force in the X prime. Do the same thing in the Y prime direction. I've got NA and W are my two unknowns, solving simultaneously. Okay, and finally, get down to the fun ones now, right? 8, 9, and 10. So 8, we've got a couple of bars here. We've got a piece of fishing line here at B, just a little fluid in tension. We think of C and D as being little rollers. We're trying to find the maximum force that P that can be applied essentially without that fishing line breaking. So you're going to need two free body diagrams. You can either use, what I used was the lower one and the overall, or you could use probably the lower, maybe the upper and the overall. You're going to need two free body diagrams. With the lower one, I only have two unknowns. Because I literally just have where that roller is sitting upon it. I know what the tension of that cable is, that's my maximum, and dy. So since I'm going to use the lower and the overall one, what I need to do is just find dy. So if I sum moments about C, that will give me dy. So then I can go to the overall one. The overall one, now I know dy. This becomes internal here, so there's nothing that happens at B or C, because that's internal now to the overall. I have two unknowns here at A plus P. Well, if I sum moments at A, those two really don't come into effect. But the moment equation, I can find out what P is. On to number 9. Bolt cutters. Something none of you have ever used these for anything illegal, right? So when you have bolt cutters, basically, in these machine type problems, you just have to take it apart. Okay? So when I took it apart, the top and the bottom are essentially symmetrical, so either the top or the bottom. So I've got kind of, I don't know what you want to call this, I'll call this the jaw, this upper jaw. And there's a pin at B. There's a two-force member here at A, AE. And then there'll be where that crushing force is, or that cutting force, I guess I should call it. Then my other member here, we've got the, I'll call this the handle. We've got the force on the handle. Technically, we'd have two unknowns here, Vx and Vy, but we're going to find out real quick over there that Vx is 0, so that's why I only drew one here. I started with one on the left. And we would have two unknowns here to C. So really, I have more unknowns than I can start with here. I have four unknowns here initially. So I start with the one on the left. By starting with the one on the left, if I sum force in the x direction and find out Vx is 0, now I can go to the one on the right.
What's going on right there? Is that like AD?
Right here? Yeah. I'm just calling that AD and saying that's a two-force. Sorry about my writing. So since Vx goes out, now I have three unknowns here. Remember, really, what I really want to get is I want to get F. So I really don't care what Cx and Cy is. So if I sum moments at Cx and Cy, I can get Vy, which is what I did. Equals 29, 25. And then, what I'm going to do is I'm going to go back to the first free-body diagram. Now, you can solve for every unknown. That would be fine, but I'm just trying to show you a little more direct way just to get to the unknowns right here. From Vx to Vy back to F now. So go back here. And I sum moments about A, since I know Vx and Vy, Vx is 0, I know Vy's value, I can sum moments about point A to get F. Question on this one?
You have to take into account when you're summing moments about A to plug in the 72 or 75 pounds.
Are you talking about in this diagram?
Well, yeah.
Oh, you don't see the
never mind.
second
Okay,
So the way I've got it organized here, these two sets of equations are using this free-body diagram on the left, and this equation is using the free-body diagram on the right. So that's with one place of 75. So the 75 gets felt in what Vy is this biggest factor. Okay, last one here is 10. We have two blocks. We're pushing on it. We want to find out, let's see here, the largest value for each no slipping the curves. In other words, where is one block or the other going to start to slip? And pending motion at either A or B. This is pretty similar to what we did in class, I recall. So I've got really three different possibilities for free-body diagram. I can look at block A. I can look at block B. And the three bodies of those. But the other thing that I did, and I think the one we did in class was very similar to this, since those are two-force members, I can kind of look at that as a joint and a truss in terms of analysis, or do a fourth triangle on it. What I can do by doing this is I can eliminate some unknowns, so I can get both A, C, and BC in terms of P, which will make it easier for me to do my comparison. And that's what I'm really doing. So that's where I started. So I drew just that joint. Right there. So 70 from the horizon, 30 down below it, 60 over here. Some forces in the X and Y direction. I didn't write too much of that out. And solve for AC and BC in terms of P. So I'm keeping P along as a constant. Okay. Now by doing that then, when I get over to this side, I'm going to substitute back in. When I get AC or BC, I'll substitute back in this value of P. If I take a look at the one on the left, plug it in, instead of calling it AC, I'm calling it 0.17P. Got my free body diagram here. And so if it slips first at A, then we would know that FA would be equal to mu times N. So I'm plugging in my mu times n value, summing forces of the x, summing forces of the y, solving those simultaneously, and I get a value of 2241. If that's not the case, then I just solve the same problem here by if it slips first to b. My guess is a lot of you probably just looked at it and said, it's going to definitely slip first to b. If these weigh the same amount, just because of the way the angle was and so forth. So you may not have even done this. You know, sometimes by inspection you can take a look at it and know for sure they're not very close. So if it slips first to b, F equals mu n here, some forces in the x, some forces in the y, solve them simultaneously so I get a different p value. This is smaller, therefore this is where it would slip first. That would be the limiting factor. As long as I push where it's 127 pounds or less, it should stay put. If I do more than that, or try to do more than that, B is going to move first. Questions? They all look like we're kind of comatose today. Is that fair to say? About how we're feeling? Okay. All right. Same off.